Today, on how it's made. Ski goggles. Tower cranes. Porcelain figurines. And diesel engines. Fog and blinding snow can obscure the view from the top of a ski mountain, but a good pair of ski goggles can add some clarity to the situation. They shield the eyes from the elements, and certain lenses add contrast in low light to allow the skier to see the bumps and dips ahead. Goggle lenses come in different tints to adjust for specific weather scenarios. They start with this injection molding machine. The operator sprays a non-stick substance into the mold and closes the door. The machine sucks up urethane pellets, then melts them into a thick liquid to mold into goggle frames. It takes just seconds for the shape to harden. A worker clips away unwanted bits, and then he's ready to give these goggles a more graphic look. He immerses the cellophane-like film, printed side down, in a mix of water and solvent. A chemical reaction lifts the graphic design off the film and suspends it in the liquid. He sprays solvent on the other side to both activate a bonding agent and dissolve the film. He then immerses a rack of goggle frames in the floating graphic. The surface tension of the water causes the graphic pattern to wrap around the frames, and the bonding agent makes it stick. This technique is called hydrographics, and it's a good way to transfer a pattern onto a three-dimensional surface. He washes away any paint or dirt from the surface of the frames. A clear lacquer is the finishing touch. For an understated look, there's always monochromatic white. A worker applies glue around the vents of a pair, then presses foam onto them. The foam will keep snow out of the goggles, but allow air to be vented to prevent fogging. He applies thicker foam around the perimeter for a weather-tight fit on the skier's face. Once the straps are installed, the goggles are ready for the latest innovation, a microelectronic fan. It will pull warm, humid air out of the goggles to further prevent fogging. He screws the mini fan to the frames and listens to its spin to confirm it's operating correctly. Next, a machine cuts shapes out of polycarbonate to make lenses. Then the special press applies heat to bend the lens. This shape will make it easier to secure the lens to the frame, and it also reduces optical distortion. Production now moves to this liner-backed foam with pre-cut lens patterns. The worker peels off a strip to expose a goggle-shaped strip of foam. She then presses a colored lens onto the strip. High-strength adhesive on the foam bonds to the lens. She pulls away the rest of the material, leaving that narrow ribbon of foam. It will serve as a spacer between the outer colored lens and an inner clear one. The space between the two lenses is a buffer zone to prevent condensation buildup and fogging. Now they shoot a steel pellet at a randomly selected pair of goggles. It doesn't shatter, which means it will effectively shield the skier's eyes from sharp objects like tree branches and ski poles. It's time to snap the dual-layer lens into the frame's molded groove. A UV mirror coating has also been applied to protect the eyes from the sun's rays and reduce glare. These goggles have everything covered, leaving the skier free to focus on the thrill of the ride. A tower crane moves building materials up to construction crews working above the ground. The operator's cabin is near the top. Just above that is the jib, which hoists the load and trolleys it back and forth. The jib and cabin rotate on a turntable called a slewing platform. A crane's tower is modular, meaning the more tower sections installation crews add, the taller the crane. At the crane factory, workers construct the slewing platform by welding together huge steel plates and square tubes. Welders also fuse sections of ladder to sections of safety cage. Then they weld each ladder and cage unit to a tower section. Throughout the assembly process, robots perform the simpler welds. Once all the crane's structural components are welded, they go to the paint shop for an anti-corrosion primer, then a top coat of paint. After each application, the part dries in an oven for about an hour at 80 degrees Celsius. The slewing platform sits on a turning mechanism that consists of two concentric rings with ball bearings in between. Computer-guided machines grind teeth on the outside and grooves on the inside, in which the bearings will ride. After lubricating the grooves, workers install the outer ring around the inner one. Then they fill the groove with steel balls and high-strength plastic spacers. This allows the outer ring to revolve smoothly around the stationary inner ring. The operator cabin is made of steel panels. It's integrated into the slewing platform. The cabin's large windows enable the operator to view how the jib is maneuvering the load. The crane's controls are built right into the cabin seat. The seat itself is designed to be as comfortable as possible because you can't step out of the cab to stretch your legs. A motorized gear rotates the slewing ring, which rotates the slewing platform supporting the crane's cabin and jib. The factory's computer-guided machining equipment makes all the parts for this gear, as well as for the gears which enable the jib to hoist and trolley the load. Workers assemble the slewing gear and mount the motor that drives it. Then they connect the slewing gear to the slewing ring and mount the ring on the slewing platform, into which they've installed the cabin. An automatic greasing system keeps the ring's teeth lubricated as it rotates the platform. After an extensive test, they install the tower head on top of the cabin. Now this entire slewing unit goes off to the construction site. After anchoring the crane's base, the installers use a mobile crane to mount the slewing unit on the tower and the jib onto the slewing unit. Then they add tower sections to build the crane to the required height. An elevating device lifts the slewing unit, clearing enough space underneath to insert an additional tower section. They connect the tower sections with giant, high-strength bolts. Then repeat this procedure until the crane is as high as it needs to be. Once the crane is fully erected, the operator climbs the tower ladder up to the cabin. As he works, he observes what he's doing through the windows. He also watches a computer monitor, which displays how the jib is hoisting, trolleying, and depositing the load. He can communicate with the ground via phone or walkie-talkie, so things are never left up in the air. Europe is renowned for producing magnificent porcelain figurines, even though it was the Chinese who invented this fine art. In 1718, the first European factories began making ornate porcelain objects, collections of which quickly became a status symbol among the nobility. This Viennese palace is home to Europe's second oldest manufacturer of handmade porcelain. Following photos of a subject, a modeler sculpts a three-dimensional figure out of clay. Not only must he include all the intricate details, he also has to make the model 14% larger than the final size, because porcelain shrinks during the firing process. He uses the model to cast a master mold out of plaster. From the master mold, he casts a plastic mold, and from that, plaster production molds with which to cast the figurines. In its raw form, porcelain is a paste which contains water, the minerals feldspar and quartz, and white kaolin, a type of clay. They water down the paste into a liquid called slip, then pour it into the plaster production molds. The plaster immediately begins drawing out the water, causing a firm layer of slip to form against the mold cavity. They pour out the remaining liquid. When the slip layer is finally thick enough, they open the mold and carefully extract what is by now a figurine with fine details. More complex figurines are cast in parts, each in its own mold. The modeler carefully touches up each casting, scraping off seams and fine-tuning the details. Then he assembles the parts, using slip to adhere them together. It's critical to keep the figurine hydrated, because if it dries out even slightly, it'll crack during firing. The figurine goes through two main firings. The first time at 940 degrees Celsius, hot enough to harden the porcelain but keep the surface porous so the glaze will adhere. They inspect and dust the fired figurine, then stamp it with a coat of arms in cobalt blue enamel, the mark that has identified this brand of Austrian porcelain since 1744. Then they dip the figurine in glaze, a mixture of water and several materials, including quartz, feldspar, kaolin, and ground-up porcelain. Then into the kiln again, this time at 1400 degrees Celsius. This bakes the glaze to a glassy finish and further hardens the porcelain. The figurine exits this firing about 14% smaller as the remaining moisture has evaporated. Once it cools, they begin decorating the figurine. Using a variety of fine-tip pens and brushes, an artist paints enamel onto the glazed surface. Between paint applications, depending on the number of colors and intricacy of color blending, the figurine undergoes as many as 6 minor firings at 820 degrees Celsius. This melts a vitreous ingredient in the enamel, fusing it with the glaze. The end result is rich, permanent color that never fades. Despite its delicate appearance, porcelain is nearly as strong as steel when under compression. But it's not nearly as resistant to impact, so when handling these magnificent works of ceramic art, a good grip is highly recommended. Drivers looking for greener cars but with more powerful acceleration than hybrids deliver can opt for a vehicle that runs on diesel. Some diesel fuel burns almost as cleanly as gasoline, yet some diesel-powered cars can be up to 30% more fuel efficient than gas-powered cars, meaning they consume less fuel and therefore pollute less. The secret behind this car's powerful diesel engine is a turbocharger. It compresses the air entering the engine's combustion chambers, filling them with a greater quantity of air. The more air, the better the fuel burns, generating extra power. The engine assembly begins with a V-shaped block with 2 sets of 3 cylindrical holes called cylinders. Robots first mount a retaining frame to support the crankshaft. Each cylinder will contain a piston that moves up and down with the combustion cycle. This piston motion will turn the crankshaft, which in turn will move the whole vehicle. But first, a laser beam device owns the cylinders. The laser's heat melts the surface of the inner walls, smoothing them. This ensures the pistons will move with minimal friction. Meanwhile, a robot oils up the crankshaft's main bearings. Then, once the cylinder honing is done, workers install the crankshaft at the bottom of the engine block, locking it in position with the retaining frame. Now they flip the engine block right side up to install the pistons, which are already attached to connecting rods. Once all 6 pistons are in, they turn the engine block upside down again and fasten each connecting rod around the crankshaft. Next, they connect the chain drive to one end of the crankshaft. The chain drive operates camshafts that open and close the valves on top of the cylinders. Those valves are located in these cylinder heads, 4 valves per cylinder, 2 through which air enters the combustion chamber, and 2 through which exhaust exits following each combustion cycle. Workers flip the heads upside down and insert long bolts. Then they position the heads over the cylinders, aligning the bolts with holes in the engine block. Robots drive in the bolts to a specific tightness. This caps each cylinder, closing its combustion chamber. Next, workers install a fuel injector into special shafts in each cylinder head. Injectors shoot a specific amount of fuel into the combustion chambers at precisely the right time. These cutting-edge piezo injectors do that multiple times per cycle rather than just once, making the combustion process much smoother. The engine, therefore, is quieter and pollutes less. The next component is the air intake manifold. It goes on top of the engine. Air enters on the left and, as this animation shows, runs to the intake valves on top of the cylinders. It's time to install this engine's secret weapon, the turbocharger. It contains 2 turbine wheels that spin at nearly 200,000 RPM. One turbine compresses air entering the air intake manifold. The other draws out the hot exhaust and sends it out the car's exhaust pipe. The turbocharger sits at the rear of the engine block, in the V between the cylinders. Over at the testing department, technicians analyze the engine's performance, in particular its torque, which determines how much power the engine can produce. Next, the engine goes into a test vehicle, which runs through specific driving cycles that simulate both highway and city conditions, all the while collecting the emissions exiting out the exhaust pipe. This test ensures that the engine meets or exceeds all the emission standards. Not only does a turbocharger give the car better acceleration, it also solves a common problem in high-altitude regions, where decreased atmospheric pressure slows non-turbo engines down. Because turbocharging compresses the air going into the engine, even at high altitudes, the car drives at full power.